Hello everyone, I am Dr. M. Malarviri, working as an assistant professor of physics in K.S.Rangasamy College of Technology. In this session, we will explore magnetic and dielectric materials of Module 4 of the course Physics for Electrical Engineering. We will cover magnetic classifications, polarization types, their dependence on frequency and temperature, and their practical applications in devices like capacitors and transformers. First, we will see magnetic materials. Magnetic materials are those influenced by a magnetic field. Some even retain magnetism after the field is removed. It is useful in devices like transformers and motors. They are classified based on how they respond to magnetic fields. The first one, diamagnetic materials, it is weakly repelled, no retained magnetism, example copper, bismuth. The second one, paramagnetic materials, it attracted in a weakly manner, it do not retain magnetism, example aluminium, platinum. Third one, ferromagnetic materials, it's strongly attracted, it retains magnetism. It is used in permanent magnets, example iron, cobalt and nickel. Next, dielectric polarization. Dielectric polarization occurs when an electric field causes the positive and negative charges in a non-conducting material to shift slightly, forming electric dipoles. This behavior affects how the material stores electric energy. There are four types of dielectric polarization. The first one, electronic polarization. There is a displacement of electrons around the nucleus. The second one, ionic polarization. There is a displacement of positive and negative ions. Third one, orientation polarization. There is an alignment of permanent molecular dipoles. The fourth one, space charge polarization. That is a charge accumulation at boundaries or defects. First, we will see the first one, ionic polarization. Ionic polarization occurs in ionic crystals like NaCl, that is sodium chloride, when exposed to an electric field. The positive ions shift in one direction, negative ions shift in opposite direction. This separation creates a dipole moment. This equation creates a dipole moment. The second one, electronic polarization. In electronic polarization, the nucleus and electron cloud shift slightly in opposite directions. This happens in all dielectric materials. The induced dipole moment is proportional to the electric field. Electronic polarizability is independent of temperature and proportional to atomic volume. Third one, orientation polarization. This type of polarization occurs in polar molecules like water or ammonia, which have permanent dipole moments. Before applying an electric field, dipoles are randomly oriented. After the field is applied, they align partially in the field direction, resulting in a net polarization. The last one, space charge polarization. This form of polarization occurs in heterogeneous materials or at grain boundaries and defects. Charge carriers move and accumulate at these sites, causing polarization. It's a common in semiconductors and ceramics. Next one, frequency and temperature dependence of polarization. First, we will see the frequency dependence. As frequency increases, heavier polarization occurs, like space charge and orientation cannot follow the alternating field and drop out. At very high frequencies, only electronic polarization remains. The next one, temperature dependence, affects orientation and space charge polarization due to thermal motion. Electronic and ionic polarizations are temperature independent. Next, we will move to applications of dielectrics in capacitors. It increases capacitance by reducing the electric field strength. Commonly in capacitors, a dielectric is the insulating material between plates. Example, ceramic, plastic film, mica and glass. Next, applications of dielectrics in transformers. Dielectrics are used in transformers for insulation and cooling. Transformer oil insulates and removes heat. Solid insulators like paper or Nomex separate winding. There is applications or preventing arcing, high voltage transmission, providing mechanical stability and insulation. That concludes our discussion on magnetic and dielectric materials. These concepts are vital in modern electronics, energy storage, and electrical engineering. Thank you for joining. Keep learning and experimenting. Thank you.